Hello. So this talk is called Scalable Internet Architectures. I've been giving this talk in one flavor or another for about 5 years, and at some points it gets a little tiring to give the talk, but a lot of the advice in there doesn't really pertain to a specific technology. It's not a specific implementation. It's really a strategy for solving large-scale problems and understanding what you don't know. So very briefly, before we dive into topic, I'll tell you a little bit about me. So I'm the author of a book called Scalable Internet Architectures. Clearly, I don't have much cleverness when it comes to naming my presentations. I'm the CEO of OmniTI. We're about 50-person consulting company that focuses on large-scale internet applications. I'm an engineer. I've been an engineer for a long time. I was an academic before I was an engineer, and then I got kicked out of academia for not being academic enough. But I find that to be a really good engineer, you have to respect the academic roots, where things come from. So I'm a big advocate for engineers participating in a kind of pseudo-academic industry groups. So on the really kind of ad hoc end of that, that's things like Linux user groups, because you get people from all varieties, or whatever your user groups are, MySQL user group, Postgres user group. But on the more formal side, you have things like the IEEE and you have the ACM. I'm a pretty heavy participant with the ACM. I'm on the editorial board of the Q magazine, which is ACM's academic magazine for practitioners. So it's basically where they compile all sorts of interesting engineering information and how it might apply to someone who actually has to do something for a living. So I find that participation in those is really, really valuable to forwarding your career and making really good decisions and staying enlightened. I work on a lot of open source software. Probably have touched source code and had contributions to around 70 different open source projects, from the Linux kernel to the Solaris kernel to Apache and all sorts of other stuff. And I have experience. So the reason that people come and ask people in our organization to talk, we have people that have spoken around the world for the last 7 years at probably about 140 or 150 speaking engagements. The reason they ask is not because we're awesome. It's because of the type of experience that we have. Because we're consultants, we don't do the same job for 7 years. We look at scalable architectures in the health and human services industry, the search industry, the lottery industry. So looking at all of these problems, everyone has a different perspective. And as consultants, that's one of the coolest parts of the job, is that I get to see all of those different perspectives, all the different approaches to problems, and people do not approach the problems the same way in those different industries, which is really interesting, because if you go into, say, social networking industry, which you're all very intimately familiar with, the approach to scalability problems within that sort of enclave is very similar from company to company. Everybody has their little secret sauce. They use different languages, different implementations, but the strategies that they use tend to be very much the same. The way they get to 10 million users, the way they evolve to 50 million users or 200 million users. And the reason is because they're usually not doing it at the same time. So you're at 20 million users and you look at your two competitors here and your 3 competitors there, and you say, what can I learn from the ones that messed up? What can I learn from the ones that did well? And you adopt the same strategies so that you start to look a lot alike. So we've seen a lot of catastrophic failures in every industry. So it's an interesting perspective on things. And I think that's one of the things that Noah is going for in the Tech Talks, is to bring outside perspective in. It's interesting to watch things fail, and that's what interests me. No one should fail, but the pathology of failure drives what we do. It's very interesting. So what's this talk about? It's talk about scalable internet architectures. First thing we'll do is define what an architecture is. We'll understand what it means to run a scalable architecture. And then we're going to talk about some practical scaling techniques. If I start to run low on time, I'm probably going to skip some specific aspects of those that I think that they don't apply to LinkedIn as much as other content companies. And then we'll touch on decoupling techniques. And then the favorite section, which is bad ideas. So the architecture, it's the whole enchilada. So a lot of times when we go in and talk about architecture, we'll come in and do like a diligence session where we'll sit with people and they'll describe their architecture. And we spend a day talking about data architecture, or a day talking about network topology and services architecture. It's like, I want to talk about architecture, not little bits of architecture, the whole architecture. So an architecture is poorly defined. If you look in the dictionary, it's almost like defining a word with a word, or defining a word with nonsense. Carefully or complex or carefully designed structure of something. That's really useless. It's an ambiguous thing. In computing, it's the conceptual structure and logical organization of a computer or computer-based program. That doesn't really mean anything either. It's really hard to get any meat out of what that is. So whoever came up with that should probably be paid less for the next definition they come up with. So an architecture is all-encompassing. Okay? It goes all the way down to space, power, cooling, choice of geographic location. And those things also include not just the choice of geographic location due to power and space costs, but also things like legal requirements. I mean, if you have content and you think that it could be subject to different jurisprudence, right? You have one deployment in one state and another in another country that you think have very different procedural laws for digital copyright enforcement, right? Those are the types of things that are important to an architecture, as well as the obvious things that people think about, like servers, switches, routers, load balancers, and firewalls. That's the stuff that pushes all the bits through. The wires, obviously, as well. Then you have, that sits on top of that, you have databases and non-database storage. And that's kind of an all-encompassing grab bag of things. It's relational databases like Oracle and MySQL and Postgres. It's the new, actually very old key value store systems that people are starting to distribute with like consistent hashing methodologies and calling them NoSQL now. Everything gets a new name. It's the same technology reapplied. And then there's just non-database storage like file systems and NFS and volumes. Then there's the dynamic applications. This is the place where people get to mess up the most, because this is the part that doesn't exist at all when you build something, right? This is all the magic juice. When you look at a company that has an engineering staff of 100 people, chances are 85 of them or 100 of them are focused on this part of it. And this is the part that makes you LinkedIn, for example. And then you have the architecture that you export to the user, and people chronically forget about this part. You're sending them JavaScript. You're sending them AJAX requests, JSON, XML, there's Flash. There's a whole bunch of your architecture that delivers user experience that gets sent down the pipe to your user and run on a machine you don't control. So that is absolutely part of the architecture as well. Because if it doesn't work, your architecture doesn't work. So why is all this important? It's because awareness of architecture is really key. So how many people intimately know all of those things in the room? Maybe one, maybe two. Usually it's not. I mean, a lot of people, they'll work and they'll deploy their apps, and they don't actually, you ask them one day, so what OS do you run on? And they'll say, oh, it's Solaris or it's Linux. Like, is it virtualized? And they're like, I actually don't even know that. I wouldn't know that because the ops group may have virtualized it without telling me. So people don't even know that, let alone where their servers are in the world. So I've seen people do network tests, and they're like, it's like 30 milliseconds of latency. Yesterday it was 15. It's like, hey, guys, we moved data centers. It's not in the same place anymore. It's like, speed of light, That sort of thing, it glues it all together. And not all of those people do all of the things. So lack of awareness of all the other disciplines is a really bad thing. And I find that to be culturally consistent across almost every organization that I visit, is that, sure, not everybody knows everything, but they're not aware of everything either. They just think, that's not my job. That's not what I do. That's not what I was hired to do. I was hired to do J2E app development. I was hired to do operations or provisioning. And they don't think, hey, I really want to know what my data architecture looks like. I want to know where my machines are located. Even if I don't influence it or I don't control it, I still need to know that information. Because when you don't, it leads to really isolated decisions. So you have people making decisions about how an application is developed when they don't control the database layer underneath. So you see people doing things like putting sessions. This is one of the common easy mistakes, is to put session cache in a relational database, which, you know what, if you have 100,000 users, who cares, right? You just put it in there and it goes just fine. When you have 1 million users and you're doing 10,000, 20,000 hits a second, a relational database costs a lot of resources to actually service requests to insert and pull out and select out the session key. And when you think, Well, yeah, I need to put it in the database. Well, you need to put it in a data storage mechanism, but do you really need atomicity and consistency and isolation and durability for session cache? Maybe you need it a little differently. You can relax the constraints, you can choose a different system, and that makes a lot of sense when you get big. So you make isolated decisions. Sticky sessions and load balancers is a classic example of that as well. So it leads to unreasonable requirements elsewhere. So you end up saying, well, I'm storing my sessions in a database, so now the database needs to do 100,000 transactions a second. And what do the database engineers hear? They don't hear, I'm storing my sessions. They hear, we now have a requirement for 100,000 transactions a second on the database. And they go, great, I have a bigger budget. And they go buy bigger equipment, and they just do this sorts of thing, and they're all in isolation. And the things are extremely over-engineered because of this. You engineer products to solve problems that you shouldn't have in the first place. Stupid decisions and absolutely catastrophic failures. Like an entire architecture that almost needs to be scrapped because along the way people were making really isolated decisions. So running operations is serious stuff, right? If it's not serious stuff, this is not the presentation for you, right? The business has to be up, you lose money when it's down, people's services are damaged. It takes 4 things. It takes knowledge and tools. Those are really obvious, right? Knowledge is what you learn by doing things. It's what you learn by studying, reading materials. Tools are the software products you use. It's Java. It's your IDE. It's your deployment platform. That's definitely not enough because that's exactly what defines a really junior employee. Like a junior person who's an engineer basically knows how to use a hammer to drive a nail. They have no idea where to put the nail. They don't know why they're putting the nail in, right? All of that stuff. And you can do that. You can run an organization that way, but you don't ever want to leave anyone at that level. They need to grow up. It takes experience. Experience is growing up, right? And more importantly than that, and what is entirely absent in the operations of the web, and not in every company, the larger the company, the more successful they are, they've learned this the painful way, but it takes discipline. And that's something that engineers appreciate, but I think a lot of coders and a lot of rogue cowboys that are like, I'm going to go fix the problem, I'm going to write some awesome code, I'm going to be clever, they don't always think of the discipline aspect. So, how do you get knowledge? This is the easiest one because everyone has an education. You read, you study, you leverage user groups like Sage or Lug or OSUG or PUGs or development groups. This includes academic groups like ACM and IEEE, and you participate in the community, right? If you're writing tools, you guys use Java here. What build system do you use? Ant, Maven, something like that? Ant. So, I mean, are people here on the Ant mailing list? I mean, I'm sure there are some people here to understand how that tool works. It's integral to your architecture, participating in that community, understand where it's going, learning where the features are going so that you can share it with your peers. So you can you're definitely large enough to have your own user groups. I mean, you see companies, even as small as ours, that have like a reading group, right? They'll read like sci-fi or something and they'll sit down at like 6 people. And yet you don't see them have a user group around like code management tools. And all of them know these things, but they don't ever share them because they don't have a reason to during the course of their job. Yet when they share them, they're much smarter for it. The other is tools. Tools, how do you learn tools? There are far too many tools in the world, right? So you have to try new tools, but it's impossible to try all the tools in the world. And the way to do that is to collaborate, participate in communities, and then you can learn from the people that you trust what's good and bad about various tools. So when you think about, I don't know what version control system you use here. Anybody? Subversion, right? So is Git better? Is Arch better? Is Mercurial better? Yes is the answer to all of those, and no is the answer to all of those. And who cares is really the more answer. Does it work? Subversion works for you guys. I'm sure it works for you guys. It's just a tool, but learning about the others and understanding the differences can really help. So we see a lot of companies that use Subversion, and they dedicatedly use Subversion, and all the developers are actually using Mercurial, right? And they think, oh my gosh, we should change to Mercurial, and it's like, why? Why? Your developers are happy. They're productive. You're getting your needs met by Subversion. Subversion has some really interesting properties that are very appealing to corporations. Like you have one centralized mainline of development that someone understands and controls. And Mercurial doesn't have that. It's kind of more distributed like Git. But the developers need a Mercurial to do their own internal development, do their own branching on the machine that they're working on. You know, if that's a productive means of use of version control, then do it. But you'll never find out unless you try. And having everybody here try would probably be a big waste of time. So you'd have a couple people try and see what their experiences are, the ones that are interested, obviously, because if you're not interested in doing it, you're probably going to do a really bad job. And try those things and share. So the one thing about tools, and this goes mostly for troubleshooting, is that it's absolutely imperative that you understand how to use your tools. You have to know how to use them when you don't have to use them. You need to use them in the normal course of business. You need to be comfortable with them so that when things go wrong and you need to use your tools, that it's not a learning curve. The last tool in the world that you want to be using as an operations engineer is man. All right? You should have used man when you didn't need to use man. You should be using the tool, TCB dump, snoop, strace or truss or whatever it is. You don't want to be looking up the flags for those. And also, you don't want to be trying to understand what the output should look like. So I have some theories on tools that are rather unpopular with the zealots because the whole VI Emacs war is repeated through everything, right? Everybody's got an IDE preference. Everybody's got a version control preference. So one of my favorites is George Weilacher, who said, one only needs two tools in life, WD-40 things to make things go, and duct tape to make them stop. Right? This is really a horrible quote in a lot of ways because this should never be someone's philosophy on tools. Yet, anybody who has come out of an emergency, emerged and survived out of emergency, there is a tremendous amount of truth to this. Is that when something is broken, it doesn't matter why you got there right now. It matters that you survive out of it. So whether it's duct tape, WD-40, or both of them to get you to the end, you use it. You learn from it, and then you figure out and you do root cause analysis. Do you guys do like sophisticated root cause analysis here for failures? Anybody? Ops? Postmortems. So you do a postmortem, and basically you identify the root cause of the failure, and you plan, and you understand, wow, that was awful. How do we not get there again? And sometimes that works, and sometimes it doesn't. But the important part is that you survived it. Benjamin Franklin said that man is a tool-making animal. Thomas Carlyle said man is a tool-using animal. One of my favorites is Thoreau, who said men have become the tools of their tools. And my favorite is Emerson, who said all of the tools and engines on earth are only the extensions of man's limbs and senses. Which means that it doesn't matter if your tool is better than someone else's. If they are better engineer than you, they will be more successful. It's about the craftsman, not the tools that the craftsman uses. So tools are just tools. They're absolutely necessary and essential to doing your job. They will never do your job for you. This is a common misconception. This usually like junior, mid-level operations engineers, they end up building all these clever tools to do their work for them, right? Okay, so that was the first part of the job, was to do that. Now they have the free time to do the real part of their job, right? So as soon as you have a tool that will replace what you do, you either don't have a job or you have a good job, which is doing all of the more interesting things. They will never replace experience and discipline, which is the part that I find most frustrating about the zealots about version control, where it's like, oh, you have to use Git because it's better. It's like, if you don't have experience or discipline using doing software engineering or release management, those tools are not going to fix that problem for you. They will help you, but they will not fix the problem for you. People did brilliant release management on FreeBSD using CVS for ages, and it was brilliant, and they did an excellent job. So they knew what they were doing. It was experience and it was discipline, a lot of discipline. Tools can help you maintain discipline. So experience. Experience is what enables you to recognize a mistake when you make it again, right? Is there anyone so wise to learn by the mistakes, to learn by the experiences of others? The answer is rhetorical, is absolutely not, right? You know, if I burn my hand and run around screaming in the kitchen, my daughter's is going to think it's funny, right? They're not going to say, wow, I don't ever want to do that, right? So they're going to grab it and they're going to run around screaming, and then they won't do it again. So occasionally you can learn by the anecdotal evidence of others and the failures of others, but a lot of times you have to experience it yourself to learn from it, which means that you have to build an environment where mistakes like that are okay, that don't damage the business, because if nobody can mess up, then nobody can take risks and nobody can get ahead, right? You gain competitive advantage as an organization by taking risks on all levels, but they're controlled risks. So you have to have an environment that's safe for risk-taking. Good judgment comes from experience. Experience comes from bad judgment. The only bad judgment is the same bad judgment made twice. And in a lot of ways, it's entirely inexcusable. So we have, at our company, we have an interesting interview question. So one of the things that I say is that you judge people on the poise and integrity with which they remediate their failures. Right? If people make the same mistake twice, it's very clear they don't learn. People who don't learn are less useful than people who do. It's a generic statement, but it's based off of equality, right? If you don't learn, you don't learn. So the key is to make mistakes in such a fashion that you can actually learn from them and not repeat them. So when you make a mistake, don't go, oh, that was dumb, I won't do that again. Like, think about it. Think about why you made the mistake. Think about the ramifications of it. Because if you don't understand the damage caused by a mistake, you're likely to not learn as much from that incident. Our first interview question, which had to be revised from HR, which was, what was the biggest mistake you've ever made? Which is a really bad question to ask, and has been revised to, what is the biggest technical mistake you have ever made? Because the whole naked, tied to the Brooklyn Bridge answer, which I got from one person, was not, there's no poise and integrity recovering from that regardless. So the biggest mistake we ever had was somebody messed up some code in a payroll system and deprived like 650 employees like 4 or 5% of their salary for 6 months before anyone noticed. So, and this was in Cold War Russia. So like, they needed their money. They weren't, it was a serious issue. And the question was not like, oh my God, I'm not hiring you. Like, I can't afford to have somebody who makes that sort of mistake. It was, how did you fix that mistake? And they're like, well, I fixed the mistake. I got all their money back. And I told told the manager what I did. And I insisted that I personally apologize to 650 people. And then I offered to resign. And that's poise and integrity on handling a failure. So, and I've never seen that person ever make a mistake like that again. Clearly, because they don't touch payroll. So, discipline is interesting. It's important to any job. So when you look at the knowledge, tools, discipline, experience, mantra, those 4 things, they have nothing to do with being an engineer. They have to do with being employed, right? Having a career, having a passion. Like, in order to be good at something, you need those 4 things. So discipline is controlled behavior resulting from training, study, and practice, right? It sounds like a martial arts book. Actually, I stole most of this from a martial arts book. So in my experience, this is one of the most frequent ingredients that's entirely missing from the field of web operations. People are sloppy cowboys. They want fame and glory. They roll out code. They realize they can fix it in production. It's not shrink-wrapped software, so if I ship it, I can always fix it after I ship it. That sort of mentality, while all of the things are true, leads to like a wild, wild west attitude when you develop. And that's really the antithesis of discipline. It's caused by a lack of focus, laziness, and people viewing it as a job instead of an art. So if you assemble furniture for a living, you can still treat it as an art and not a job. If you build furniture for a living, you can treat it as a job and make junky furniture, or you can treat it as an art and make beautiful furniture. So it's just like programming. You can be an engineer or you can be a coder who writes code. An engineer solves problems with code. You have to treat it as an art. And in any trade, back to the martial arts book, it's to be excellent, you have to treat it as a craft. You have to become a craftsman. You have to learn discipline through experience, and through practice achieve excellence, right? And that's That's like if you want to be a mathematician, if you want to be a coder, if you want to be an engineer, if you want to be a race car driver, whatever it is, that's how you become excellent. So that is the philosophy lesson. And then we'll get into actually like, hey, web stuff. That's what we do. So what do you need to know from day to day to run a large business on the web? And the answer, first and foremost, before anything happens, is version control. Basically, what's that? Hallelujah. Version control, there's one other thing, which is monitoring, but there's only so much time. So version control, a lot of people have version control in the documentation arena and the application code arena. Now, why? Because version control was originally designed to revise files. Files end up being code. There's no super duper metadata system for code, really. It's not like a Word document. It's usually a text file or something like that. So version control systems are good at managing text files. And they're good at managing application code, and application programmers realized that and evolved the tools to be even better for code. So the tools today for version control systems work really good for application code and happen to, as a side effect, work very good for documentation. They're not so hot for the rest of these things. So monitoring configuration, application configurations, and systems configurations are actually not that hard to put into version control because those systems can run like a binary, like Subversion. They can run a Subversion client on them. You can very easily integrate a strategy for putting your configuration files and any changes to the system into a version control system. Firewalls, routers, and switches tend to be more black box appliances, and it's very difficult to get the configuration information, settings changes, and things like that out of them to put in version control. And if it was easy, my daughter would do it. She's 4. So just because it's not easy doesn't mean it's not part of your job. You have to do it. It's your job, right? You put your switch configurations, you put your router configurations, you put your firewall configurations, and they're all in version control, and they're all accurate. And that's it, right? If you don't do it, stop what you're doing and go do it. Database schema is like crazy, right? It's really hard to put database schema in version control because you don't ever edit database schema in files so much. So the most common approach that we see to that is that we'll have some sort of schema basis that's dumped into version control, and then you have basically a directory for going forward and a directory for going backwards. And every time you launch something, you put a migration script in the forward, and the oh no plan goes in the other directory. So when you roll it out, you run one of them, and then everything goes right. You don't use the other one, and everything goes wrong. You run the migration script backwards. That's an interesting use of version control, but it's not really versioning the database, right? Because I can't really see what the entire schema looked at any given time. There are methodologies for doing this. So what we do every day is we pull all tables, all stored procedures, all triggers, all constraints out of every database and check them into version control over top their previous forms. So we get a change set. The challenge is we don't know who did it, we don't know why they did it, but we do get a change set. We can see at any given moment, what is the state of my database? What does my schema look like? It's like a logical DDL only export. So everything should be in version control. And it doesn't matter which tool. And we use Subversion too. Yay! It's now part of the ASF. Congratulations. ASF had their 10-year anniversary 2 weeks ago. And Subversion was contributed to the incubator of ASF. It's the only project ever in the incubator that may be older than the Apache Foundation itself. So Subversion is 10 years old as well. So the other thing that you need to do is you need to know your systems. You need to know what something looks like unhealthy. You have to know what it looks like healthy, right? You go into the doctor and you limp, right? And you're like, oh, I don't feel good. He's like, of course not. Your leg doesn't work. You're like, I've had this problem for 12 years. This is not the problem I'm talking about. He's like, well, I don't know that. I've never seen you before, right? So the idea of going to someone when you're sick and asking them to tell you what's wrong with you when they don't know what you look like when you're healthy is like black magic. It's one of the problems with our healthcare system, one of the many. It's also one of the problems with people's attitudes toward healthcare. But it's the same way on systems, right? When you say like, oh, my web server's slow. Well, let me go trace the process. Let me go look at it. Hey, this is taking too long. Really? Is it taking too long? Did it take that long yesterday when everything was fine? If you can't answer that question, then you have no idea what you're talking about. Right? You need to look at all of these things. You need to know what they look like. That requires monitoring everything, collecting as much information as possible, even if you don't look at it now, because looking at a piece of information like my database is slow, let's look at the IO ops on the disk. Let's see how many IO ops it's doing. You're like, wow, 550, that's a lot. Like, really? If I compare it against a trend, and I can see that the trend of IO ops changes with my problem, then maybe they're related. So a lot of times, the whole causation versus correlation thing is what makes trending and detecting things hard. It's actually not what makes it hard, is that people don't even look. So they come in and they're like, well, I don't know if it's causation or correlation. I'm like, of course you don't. You don't have any historic information at all. You don't know anything at all. You're looking at a number that means nothing. So you have to look at everything. Two of them, probably the most widely deployed products for this are Nagios and Cacti, which I have a deep and intense hatred for. We use them. We've used them for the last 12 years. We continue to use them. But about 2 years ago, we started developing a new product that replaces those. That's open source. It's BSD licensed, called Reconnoiter. And it does all that and more. It does trend detection, fault detection, all sorts of interesting stuff. And it's designed for systems that have multiple data centers and thousands of machines. So if you're interested, you should check it out. We run it. So another philosophical question, which I'll gloss over very quickly, is package rollout, machine management, provisioning. They tell me that I should use Puppet to do that. Then they corrected me and told me I was supposed to use Chef to do that. But I stick to my strategy on tools, which is a master craftsman chooses and builds the tools he likes, and a tool does not make the master craftsman make, right? The tools don't matter so much. It's doing the job right. If you find the tools useful, then great. We have a serious problem in the industry where someone learns how to basically pound in a railroad spike with a sledgehammer, and they're like, everything looks like a nail. So then they go, do some finishing work, carpentry work with a sledgehammer, and they learn to tap it really light, and then they tell everyone else in the world that I was awesome and I did this beautiful work and I used a sledgehammer, and people don't go, I wonder if there's a better tool for that. They just say, great, he did it with a sledgehammer and succeeded, so I'm going to use a sledgehammer, and there's this weird propagation of crazy ideas. So just do something that works for you. Most large operations group that manage systems may use one of those tools, but they just make this not a problem. It's part of their job. So how do you build systems, actually build systems? Static content, we'll start with static content because it's one of the easiest things to do. It's old tricks, it's good games. You can use Akamai. Do you guys use Akamai? Yes. All right, most people use Akamai. You could use a competitor of Akamai, or you could actually build it yourself. Now you're building something different from Akamai. In a lot of ways, you guys use a relational database, of course, but you also use a key value store, correct? Yes. So why don't you use a relational database? Because you decided at some point, I want to build a database, right? Which sounds really dumb, but it's not actually dumb, right? What you realized was, I'm using Oracle, and part of the stuff that I'm sticking in Oracle, Oracle's not really optimized for. I'm paying a lot of costs that I don't need to pay. I could design a system more specific to my exact problem for a lot cheaper that works better. So I built that. You can't build a replacement for Akamai. There is no real legitimate way to build a replacement for Akamai. But saying that you need every feature of Akamai is a little short-sighted. So you can serve a lot of static content without a content distribution network, or by building one. So one of the things that's interesting about HALB, I spent several years in graduate school researching algorithms for high availability, and all the vendors, algorithms for high availability and algorithms for load balancing, and all of the vendors that sell load balancing appliances like Citrix, NetScalers, F5, Big IP, Cisco, all of those guys, they always sell these HALB devices and confuse people on what HA and what LB is. HA is highly available. So what they do is they sell you this green box, and they say it's an HALB device. And you're like, really? It's highly available? And they're like, yeah, if one of your web servers goes down, you won't even know it. I'm like, well, let's erase this guy. And they're like, well, it's not highly available itself. I'm like, okay, that's not highly available at all, right? That's called load balancing. If you just don't distribute load to a machine that's not on or available, that's called load balancing. Highly available means that if this box dies, that box can do the work. They do both of them, but they're very confused about which one means what. The interesting part about static content is that it's easy. It's an easy problem. My laptop can serve about 500 megabits of static content without sweating, right? It's a laptop. If I buy a $3,000 commodity off-the-shelf server today, I can push 2 gigabits of static content. It's not hard to do. There are good technologies for it. The problem is I can't make it available, right? Which is why I buy this really expensive device. So the interesting part there is that I don't need load balancing because 2 gigabits is a lot, right? If I wanted 5 or 6 boxes, now I have 10 gigabits. What I need is the HA technology. Well, when you look in these boxes, they all run Linux or FreeBSD, and they're all little small kernel changes and software products that provide HA and LB. So you can take the HA software product and just take it out of their web server and put it in your web server. So you can run HA on your web servers. So you set up a web server to host all of your static content called an origin server. And then you set up a handful of servers running a reverse proxy cache, something like Squid or Varnish. I heard today you guys are deploying Squid. Works well. Apache Mod Proxy. Again, the tool doesn't matter so much. You do an evaluation of pros and cons and choose one. And if you're wrong, you put another one in. It's not a big deal. So you deploy those servers. So when I hit one of those servers and ask for content, it turns around, goes to the origin, and pulls it, and then it remembers it so that the next request, you don't have to do all the work. So then I can make them redundant. And then you say, wow, that's black magic. Routers have been redundant for years, many years, using protocols like VRRP and HSRP. There's a product called UCARP as well. And then there's Whack-A-Mole, which I'm slightly biased because I wrote in grad school, that do all of this stuff. And they're all basically the same. You just use the one that fits your mentality the best. It's simple. It's easy to scale. And the way it works is that you set up, before we jump into the multiple machines, multiple data centers, the way it works is that you have a couple of machines, and you give them IP addresses that are publicly accessible. So I have machine A, B, and C, and I give them IPs 11, 12, and 13. Something, .11, .12, .13. And they may have other administrative IPs, but what happens is those 3 machines are responsible for those 3 IPs, period. It's kind of like a blanket statement. So if one of them is up, and only one of them, it will have all 3 IPs. If another one comes up, they will do some shifting and rejuggling, and one will have 2 and one will have 3. Oh, one will have 2 and one will have 1. And you might ask, well, which one has 2 and which one has 1? I don't really care which one. I think random is best, but if all 3 of them are up, each one should have 1, right? It should be as balanced as you can possibly get. So it's pretty straightforward. That's pretty much how routers do it in the active modes of routers. So what you can do now for the content distribution aspect of it is you set up 3 different data centers. And we'll give them different IP ranges, DCA, DCB, DCC, like /24s. And you have 3 machines that expose 11, 12, and 13 in each of those. And you can set up more data centers if you want, but let's do 3. So then you have your users. And your users do this thing. They say, I want to see images.linkedin.com. And they request the DNS server, and it says, hey, images.linkedin.com, this is a.b.c.11. And then the user goes and connects to port 80 or port 443 on that box and asks for an image, and it gives them to them, and everybody's happy. So the question is now, how do you get the web cluster that's closest to user 2 to be answering the questions? And the guys who invented DNS is my brain melting moment of the internet. Every once in a while, you look at something and you're like, how does that work? You're like microwaves, right? You're like, you push the button and you don't see anything go on and the water boils, and it's like, that is cool, right? DNS is that way, right? So every time, over the course of this presentation, there probably have been 2,000 DNS requests from this room, and I think there's only 5 laptops open, right? You have instigated that. All these DNS requests are UDP packets. They're not connectionful, right? I just send a question out to the world, send it to someone, but I send it out to the world, and I just wait for it to come back. And guess what? It does. Like every time, it does. And there's millions of these, millions and millions of these happening every second. And very rarely do they get lost, because your user experience would really suck if they get lost, right? It has to time out. It actually takes like 30 seconds to time out usually. So, and that rarely happens. So it just works. And then when you think about the routing changes that happen on the internet, in the course of this conversation, there's probably been 20 or 30,000 network collapses of peering points that have shifted routing traffic. Like, it still just worked. Like, it just threw something out, and then somebody threw something back to me, and I don't know where it came from, and it has the right answer. It's crazy. So the guys who invented DNS were really smart. I think it's probably the most well-built, even not future-proof, but well-built distributed system that's ever been deployed on the internet, because it just works all the time, and we still rely on it. So what they thought about was, hey, when I have multiple DNS servers out there, I'm going to ask them questions, but I'll always rotate between all of these DNS servers. So if LinkedIn has like 3 or 4 DNS servers published, the client will go to each one of them. Wouldn't it be clever if one of them's closer to us, has a lower TTL on the packet, we'll start to prefer that one? Like, these guys thought of everything. What they didn't think about is that there were like 30,000 network collapses over the last hour. So that doesn't work at all. It was a brilliant idea. It doesn't work at all. Doesn't hurt anything, but doesn't help anything either. So the question is, how do you get these people to the closest? And the answer is you use an approach called Anycast, or shared IP. So you have these 3 data centers, and then you put a DNS server in each of those data centers, and you publish the same IP address from each of the DNS servers and announce it over BGP. And what that means is that same black magic that caused DNS packets to just go out there and come back will cause user 2, when he says, what is images.linkedin.com? It will shoot the packet out, and the internet magic will route it to the closest IP, the closest path, right? Because people don't want to pay as much. Unfortunately, it's not the closest geographically necessarily. It may not even be the closest in user experience. But when you throw the packet out there, the ISPs that it goes through, all the providers, it will go the cheapest path for them, which is likely to be the fastest as well. So user 2 will send a request out. It'll hit the DNS server. And then that DNS server up there next to the blue cluster will answer the blue cluster's IP addresses. And the web servers don't have this shared IP. Only the DNSs have the shared IP. And then the quasi-magenta user 1 will hit the cayenne web cluster. Really bad colors on this slide. So, and if the internet fractures in some way and you can't see this web cluster, you're guaranteed that you won't be able to see this DNS server as well, which is very nice. It's kind of magic. If you don't have your own autonomous system number and you don't run BGP with your providers, you can use a third-party service that provides this, and there are two major services that provide this. One of them, Akamai does this, but they don't advertise it. They may do it for you. I'm not sure. The 2 that advertise it are UltraDNS, which was bought by Newstar, and Dynect, which is a spinoff from DynDNS. And both of them have a very large global footprint. I think each has between 12 and 16 data centers around the world in every place you'd care about that serve that. And you can say, hey, the one in Taipei serves these addresses. The one in Japan serves these IPs. The one in San Francisco serves these IPs. And you get to control that. Any questions on that? You guys should feel free to interrupt at any time. So far we've built our own load balancer and have to support it.
Yeah, VRRP and direct routing and stuff. I think that load balancer code, as long as you don't actually run the layer 4 to layer 7 load balancing, is pretty stable. It's old technology, it's old code, it's stable.
So the question was, so why would you build your own? And the answer is, you're sort of building your own. You're actually using the old stable technology. It's all there. You're just running it on a different piece of equipment now. You're running your load balancer on a different layer. It's the same software that you'd have to support. Unless you're talking about commercial load balancers, because when you're pushing like 2 gigabits of traffic, it's important that you have a pretty solid load balancer. And then you're starting to talk into the $200,000 of equipment range for the load balancers that do nothing but distribute the content. And the interesting part of that is that we aren't building a load balancer there because we don't actually need to balance any load. Any 1 or 2 of those machines could actually serve all the content that we'd want. I mean, like a $3,000 machine can serve 2 gigabits of traffic. You can build like a $5,000 or $6,000 machine that can serve 8 gigabits of traffic. You don't need to balance it so much. What you're doing is you're tackling an availability problem. So the problem with deploying load balancers in front of things like that, like the static solution problem, the static problem, is that you're buying and maintaining a piece of equipment that balances load when load balancing is not a requirement. So what you're doing is just moving the HA tier back. You can actually do that with routing. Chances are, so for the shared IP, none of the load balancers really do this. F5 has a product that does this but doesn't work like this and doesn't work as well. So does Citrix. So you end up having to do this if you want to do geo-local data centers anyway. If you have multiple data centers and you want people to go to the closest for your dynamic content, you'd still need to do this sort of thing. So building your own tools and having to maintain them is an interesting problem. You guys built Voltamort, so I assume that you weighed all of the challenges in that, because maintaining a product like that is a lot of work. And you guys did build Voltamort, right? Yes. Okay. Good. Everybody's nodding. Right company. There's challenges, right? You end up being put into a spot where I can solve my problem by just writing $1 million check. Or I can invest $150,000 or $250,000 in engineering resources to build something like that. In this case, you're investing about a week's worth of a single engineer's time to do all of the architecture for it, and then you're comparing that to rolling that out. Now, I would say that if you're serving dynamic content from one data center and you're serving static content from one data center, you're going to have load balancers there anyway, so why not just use them? They'll probably do the job. If you want to deploy this to 18 data centers, and now you need to buy 36 load balancers for your 18 pairs, then you're starting to think, wow, should I write a check for 36 load balancers, or should I just do this, which might be a little bit cheaper. A little bit being like either 6 or 7 digits cheaper. But it's a trade-off. It's absolutely a trade-off. And you shouldn't jump and do this if you're not pushing a lot of traffic. So I don't know how much static content you guys actually push. Anybody know that? Super secret. Not a lot. Yeah, but and is that through Akamai? From origin through Akamai on the static? It's mixed? Okay. Not a lot. So the reason this problem is easy and solved is because the porn industry solved it for us. So dynamic content. Dynamic content is more interesting. It's what makes your product interesting. Static content's only interesting in a certain industry. So dynamic content comes down to some more rules of computer science. So Donald Knuth has this famous quote that people always forget the first part of. So they always say, oh, premature optimization is the root of all evil. It's the thing you dole out when you're like, hey, that could be a lot faster. Oh, I'm not going to do it. Premature optimization is the root of all evil, right? He said we should forget about the small efficiencies, say about 97% of the time, right? If there's anyone in this room that can always accurately define which 3% that is, then you are underpaid. I guarantee you are underpaid. You should run your own company and conquer the world, right? It's not premature optimization is the root of all evil. I agree with that, but knowing when optimization is premature defines the difference between a master engineer and an apprentice. So that's a big problem. There is a solution to that, which is an interesting one. It's a documentation-driven solution. But first, the optimization comes down to a simple concept of don't do work you don't have to, right? That is the premise of optimization. And you can take that in two forms. It can take the form of computational reuse. Everybody's seen the Fibonacci example, where it takes like 48 years to calculate Fibonacci fib of 60, and it takes like 0.01 seconds to do it if you use computational reuse. That is effectively caching. But my favorite way to optimize is to not do anything at all, right? You avoid the problem. And that's the same case with like storing session caches in Oracle, right? Where I need my Oracle database to do 100,000 transactions a second. Well, the answer is no. Like, go away. Solve your problem yourself. Do it differently. And they're like, oh, I guess we could put memcache in place. I'm like, I can write a check to Oracle and get 100,000 transactions a second. I can do that. Probably right now, hardware included, would probably cost $700,000, $600,000 maybe. I could also buy 2 $5,000 boxes, run memcache on them, and have my problem solved as well. So The problem is I didn't need Oracle for that. I created a problem or an implementation of a solution that was really not required. Another great example of this, which is a great one, I love this because everybody does search. You guys do search, I'm sure, where you have this product spec come down and it's like, I'm going to type in like Bob Walters and I hit enter and it searches Bob Walters and it gives you like page 123 ... 7,132. And the product spec says that number has to be accurate. And the answer is, sure, I can do that. How much money do you have? Right? I can solve those problems. And they're like, well, it needs to be accurate. It can't be wrong. And the answer is, how much does it need to be accurate? Because if I tell you it costs $1 billion to make that accurate, I bet you're going to say, you know what, it doesn't need to be accurate. The interesting part is that number is nowhere near $1 billion. That number could be as little as $20,000 or $50,000. When you say, I could put in a 5% error margin on this number right here and not have to design this big architecture to solve the problem. And they go, oh yeah, 5%, same number. And you're like, no, it's not, because I'm an engineer and I can read, right? This is not a product spec that says if this says this number must be accurate, accurate means zero tolerance for error. So don't do that. So work. This is the problems, isolated decisions. So optimization of dynamic content really means don't pay to generate the same content twice. As bigger systems that are highly dynamic grow, this becomes much more challenging because the content, sometimes you generate absolutely unique content all the time. I don't think LinkedIn is really at that size. I don't even think, I mean, most of the sites aren't really at that size where there is no feasibility of really caching any bit of the page because any part of it can change. And I would say at this point, like, work with the product designer and the user experience designer and the user interface designer to reduce the likelihood of that, right? You want the product feature to be useful, but you also want it to be implementable for cheap. So you work with them and you say, you know, if we change this or change that on the UI side, and UI people hate it when you're like, hey, you know, we could do this. And they're like, it's my job, it's my job. I put the buttons on the page. I show you where the data goes. But that sort of attitude is the same as the Java developer or the PHP developer saying, you know, I think I really need a table structure like this. I'm the database engineer. I'm the database architect. Go away. I design the tables here. Like that sort of attitude is you know, it's stupid. So collaboration can actually simplify problems. So a real-world example of this is a news site. And this, we're going to go through this really quick because this doesn't actually apply very much to you guys, I don't think. You have a news site. Articles are stored in Oracle. There's lots of different sections. We have about 100,000 page views a second. And there's personalized information on every page. So the answer is that Oracle's fast enough to do this. This is not a problem for Oracle. It may cost a lot of money, but very rarely have I seen a problem that something like Oracle could solve. And I harp on Oracle a lot because they're probably one of the companies that I dislike the most that has probably one of the best products. They're really hard to work with as a company, but their product's really brilliant. And we try to not use it as much as possible, but you end up there sometimes because sometimes writing a $100,000 check or $1 million check is a really easy way to get where you're going now, if now is important. But we have a really easy problem, and it doesn't actually require, this problem doesn't require a database at all. We're just using a database because it's there. And if we're going to do that, why don't we use one that's free? Definitely. So updates are controlled. Updates to news items only happen through a specific workflow that's defined. The publishers produce that stuff. The update to read ratio is minuscule. This should be 1 to X, but you've all read news lately. It gets revised and no one tells you. So it's some small number, hopefully, to N. So 1 million people read an article, and it's maybe updated once or twice. And user preferences are only ever updated by the user themselves. So you stick a news item in Oracle. You write your page. We'll just pretend that has like a JSP on the end of it or something. So it's a page that pulls things from the database and shows them. And perhaps the most interesting thing on this page is the pulls user preference from cookie. Because I said that DNS is probably the most brilliant distributed system ever deployed on the internet. It's not actually true. The user's browser as a node in a distributed system is the most brilliant because it scales exactly with your user base. Every user you add, you get a new node. you're guaranteed that you have no cross-node traffic because you only store data that the user can see themselves, right? And when a node crashes, you're 100% available because they have bigger problems than looking at their cookies, right? It's a brilliant distributed system. So the idea of putting user preferences in cookies, if you don't like that, encrypt them opaquely so that they can't read them or modify them. There's a lot of ways to do this. And what it means is that you can basically take away almost all back-end data storage traffic for user cookies. You only have to refresh a database on an update, or if their user cookies get purged, you need to populate it off of a cookie populator. I hate query strings. We'll rewrite it. This actually is really valuable, and we'll see why. So the way this should work, so what happens now is when you access the page, it goes out to Oracle, it pulls the news page, it renders it in the pulls the news article, renders it in the page, and sends it to the user. So what would be much better is if the publisher, like the guy on the street taking the report, writing the article, and editing it, typed it into the PHP page. Like, from a technical engineering perspective, performance perspective, that would be brilliant. Obviously, it would be a disaster for publication, right? You cannot do that. But you can sort of fake it. Right? You can have a PHP page produce a PHP page that has the article content in it. And what that means, because RAM is cheap, when I first request the article, I don't actually have this page on disk, news items 1, 2, 3, 4, 5.html. It's not on disk. It doesn't exist. So what I'm going to do instead is I'm going to run the news article.php, the dynamic code, providing the article parameter to it. It will render it and show it to the user, but it will also generate a complete PHP or JSP page that has the article content inlined in it. So the next request that comes in will find the page on disk, load it into memory, compile it in memory, and serve it directly, which is almost as cheap as static content now. So now, every time a news article is read, the user already has their preferences in their cookie, so they don't have to hit the database for that. And the news article is only ever generated once after it's created per web server if you're not using shared storage, which you shouldn't be. So this is really simple. Now you don't ever have to hit a database again, right? So there's obvious problems with this. The biggest problem is that what if I change my article? So one question is, why should you change your article? This is a publication. You should probably submit a new one or a redacted one or something like that. They will change. More interestingly is what happens when you add a new feature. What happens when you change a template on the page and you've got all these pages that are cached there that have this stale article in them but don't have the right surrounding information, like you changed some template. And the answer is cache purging. And cache purging is actually not hard at all. Basically, you tell all of your web servers that this piece of content got invalidated and they delete it. It's not a hard problem. You can use a message queue. We built a system recently on this and dropped, they were running on a largish architecture. And with basic approach like this, we didn't use PHP, I think we used Perl. But with this caching methodology, I think we were able to serve probably about 350 megabits of dynamic content off of 2 boxes at, I don't know, something like 16,000 requests a second or something like that. It's just not that hard to actually design a system to not do things twice that you don't need to. So the idea is that you send out cache purge requests. You have basically a dependency matrix. This cached document, this compiled document depended on these includes or these modules or these technologies. And when one of them gets purged, you find all its dependencies and just flush them out of the cache. If I had to do it again, we built it on spread. Did a lot of work on spread, and I wouldn't have used it for this problem. If I had to do it again, I'd use a message queuing technology. Do you guys use message queuing here? MQ? Any type of, which one? ActiveMQ? Because you're Java shop? Yeah. All right. So ActiveMQ is good stuff. Yep. Can the system serve the full load when the cache is purged?
Yeah.
So in this system, yes. So what you can do in this system, it could, because there was a pretty steady growth rate of hot documents. So the cache purging, it collected pretty quick.
But if you change a template,
If you change a template and it blows the whole cache. So the things that you can do in that case is if you have something that has a huge number of dependencies, what you can do is take several nodes offline and put them in a private, purge their cache, and then warm them, and then bring them online again. So there are some techniques if you know that you're going to do something that hurts to spread that hurt out before it actually happens. So there are some techniques. Yeah, there are some challenges. Anytime your cache just disappears, you're going to have a really hot origin. So now the bottleneck is, so we have less database connections. This is all happy. This resonates with everybody. Now this example is in PHP, and Yahoo tells us that PHP is fine, and we believe them because they're Yahoo. So caching is really interesting. I would say, I think this is the only slide I get to talk about it on, but you guys use Memcache? Yes. Okay, Memcache is hands down the worst thing that's happened to our industry. It's an awesome product, and when used correctly, it is great. But the problem is that people don't understand how it works. They don't, not the product itself, but the concept of caching. So you're doing some work, and you're like, oh, I don't have to do this twice because it didn't change, so I'm going to cache it. And then you're like, oh, you know what? What if it does change? And then the conversation goes so wrong after that, where it's like, I don't know, let's just cache it for 5 minutes. Which is awesome, because like, can you imagine your CPU doing that? Where it's like, hey, let me pull this bit of memory out and put it in a register. Well, what if it changes back there? I don't know. Let's just pretend for a while, for like, say, 15 seconds, that it's just going to be right. Like, okay, you have a kernel panic on boot, is what you have. So the problem is that those decisions aren't bad. It's making them without understanding them that's bad. People stick stuff in caches and set timeouts and say, oh my gosh, this was brilliant. You know, I solved the whole problem. You changed the problem. That was brilliant. Not solving it. Solving it's easy. You decided that you no longer needed to be accurate. That decision, when you're allowed to do it, is the right decision to make. But you have to understand, because it's not a magic bullet. It's very different than that. When you cache things for like a certain timeout, one, you have issues when that timeout all goes down. You have like big rush on a stampede on origin. But you have changed the dynamics of the game. So we hear so many times, we do a lot of Postgres consulting, and we're like, oh, database is too slow, database is too slow. I put it in Memcache and solved the problem. I'm like, you know what? And they're like, they'll tell me the architecture, and they're like, so we do the query out of Postgres, and we stick it in Memcache with a 300-second TTL. And I was like, your original question to Postgres was not, give me an answer that may or may not be accurate now, but accurate within 300 seconds. Because if that was the question, I probably could have made that a lot faster on Postgres too. But what you did is you just changed the solution, but didn't realize you changed the problem. And that's really important. So data management. Data management is interesting. How do you scale databases? This is a challenge for everybody. And I've come up with the solution for any other database architects in the room. Yes, this is it. The first thing you do is shard your database. And the second one is you shoot yourself, so it's no longer your problem, right? So it's perfect. Well, because you get perceived value from the first one. It's an interesting problem. So really quickly, horizontally scaling your database via sharding or federation requires you to make concessions. Okay, this started in the MySQL world predominantly, and like I said, when you put caching in place, you make concessions. You change your problem. Well, MySQL had so many problems in the first place that changing them didn't matter so much. Like they didn't have foreign key constraints, so it's not like they had to lose them when they sharded. Right? If you talk to an Oracle database administrator or Postgres data, or how about any database administrator other than a MySQL one, and you say, hey, let's shard, and they're like, you know, this references that column in this table, and that data may not be on this database, the foreign key won't work. And they say, foreign keys, database integrity, whatever, doesn't matter. Right? It matters. The question is how much it matters. So a shard is a piece of broken ceramic. It has sharp edges, so sharding is a verbing of something, but you're probably going to get injured with the pieces. Databases other than MySQL tend to scale vertically quite well. And actually, the Percona guys for the MaxDB stuff, which is a MySQL fork, are stepping that in this direction. I don't know what their trajectory is, but they've done some really good things. We'll see if it maintains the good curve. But that's interesting. So a lot of times you can actually just optimize. And if you fragment your data, you will throw away any relational constraints. And this should make you cry. You should hate yourself for it. It's a bad thing. And then you should decide that you're stuck and you have to do it anyway. And it's a bad thing. We manage tons of databases that are sharded because they need to be sharded. Unfortunately, we manage a whole bunch of databases that are sharded just to punish somebody. So many times relational constraints are not needed on data. This is one of the problems why people feel like they need to shard their databases, because they're doing so much work in the database that they don't need to do in the first place. If you don't need relationships and you don't need atomicity across multiple manipulations, and you don't need durability if you don't need durability, you don't need a database. And there are some interesting technologies to do this. And my favorite one, which is really reliable, it's called files. And you can stick your data in them and read it out, and it works really well. If files don't work so well for you, there are some document-oriented databases, and there are a lot of them. And I only put CouchDB on this slide as an idea. I wouldn't deploy it just yet. We'll see if I'd ever deploy it. But the concept of the distributed document database like CouchDB or MongoDB or there's a couple others out there. So in a lot of ways, these are very similar to key value stores, like Voldemort. You're saying, I have a document, here it is, just store it, and that's it. And the other one that's awesome is cookies. And if you can ever put it in a cookie and it works for you from a semantic point of view, then you should use that. Non-ACID databases are easier to scale. The CAP theorem doesn't apply to them directly. And vertical scaling is achieved by other means. The best means of vertical scaling is doing only what is absolutely necessary in the database. So a lot of people say, I hate my database because it was working okay, but then it was a performance problem. And then I pulled all the documents out and put them in Lucene to search on them. And my database sucked because my database should have done that for me. I'm like, that's crazy, right? It's like, I tried to build my house with a electric drill, and then finally I had to build it by a saw. My electric drill sucks, right? It's like, that doesn't make any sense at all. The problem is that you were using a database for something you should never have been using it for in the first place, and you could get away with it because it was easy. So it doesn't even mean it was a bad decision. It's a bad decision to not make the change or blame the wrong system, right? You go up and you build things, and when you see pain points, you understand them better, and you fix them. So, and you run a good database that scales well. So, really quickly, if you horizontally scale, the tricky parts here is that you really need to understand the questions you intend to ask when you horizontally shard things, because you don't know where all your data is going to be, or not precisely. You have to know where your data is going to be. But when you ask a question and you do an OLTP style query like, hey, get this user's friends, it's painful to have to hit 40 nodes to get one answer back. It does not scale well. You really want to separate the traffic around, and one user hits one node and another user hits another node, but they're really only hitting one node at a time to answer your question. That can be really hard because if you split things, especially in social networks, if you split things out by user, is it the one on the left side of the relationship or the right side of the relationship? So duplicating data can actually solve that problem. Quickly, on private messages, like let's say I want to build a system where Bob sends Sue a message. Individual sends a message to their friends. You should be able to see all the messages you sent. All right, this is basically, anybody use Facebook? I hope so. You guys use, do you ever guys use booze mail? You get to send like fake booze to your friends, like here, have a shot, and then they could redeem it only if you played fair. But that was interesting. So basically, I could log in and send my friends like shots of tequila, and when they logged in or I logged in, I would see whatever was sent to me. And Facebook has 240 million users, and people send a lot of drinks, so it had about 2-3 billion rows in it. It's a lot of drinking. So users. So we shard, right? We shard by recipient, right? So I'm user ID. Let's just do like a bucket of 100. So if your user ID ends with 1, you're in bucket 1. If it ends with 33, you're in 33, right? Not a great partitioning method, but basically now I get 100 different buckets that are relatively evenly distributed. You could use a hash that's a little bit more intelligent than that, or range partitions, or whatever you want. But basically, when I show up, when I send a message, it looks at the recipient and stores it on that node. When I show up, it looks in my node and says, hey, do you have any messages to Theo? And that's easy. So now it gets interesting because now I need to be able to have a catalog of what I sent. So now, if I don't change the architecture, data architecture at all, what I have to do is when I look at what I sent to me, I go to my node. And when I look at what I sent, I do a map across all nodes in the system, get all of the messages I have sent, and pull them back together and aggregate them back together. So the easy solution to this is store messages twice. I store all of them to people, and I store all of them from people. So I go to my node, and I see all the messages I sent and the ones I received. Yes, there are duplicate copies. But storage is a lot cheaper than solving the map problem. Scatter-gather of that. This is a really trivial case. This is the one where it's like, oh man, now that the requirements change, hey, I can store everything twice. Ooh, the world is saved. A lot of problems are much more challenging to that. So for example, let's do statistics on how many messages had, hash IN in them. It's like Twitter style. That's changes. There are ways to do it, but the problems get harder. And if they were in one enormous database that could scale, the problems would be trivial the questions would be trivial to ask. So, partitioning allows you to reduce the data size. You just might cause more problems than you've solved. Complicated queries become really painful is the problem. And it's a commitment. So this is where you get to be an engineer, right? If you decide a partitioning strategy, don't just do it on a whiteboard and think it's going to work. Build a simulator. Go back to the college days and be like, let's prove the assignment right. Build a simulator, put the data in the system, do the queries on it, and make sure it actually behaves how you expect it to behave. And at least when things change, you know that it worked before. So you have to do what you have to do. Really quickly on multi-master replication, it's not there yet, so don't do it. So, networking. You guys use multi-master replication? Yes? No? No? All right. Okay, so networking. This is the part that almost everyone forgets about. I think Firebug is the most brilliant tool ever built because it makes web developers and front-end designers aware of the network level suddenly. You have this cohesive knowledge. You are aware. And awareness removes catastrophic failure. So networks are part of the architecture. A lot of people think in bytes per second. Networks don't think in bytes per second. They think of packets per second. They think of load balancer states. They think of firewall states, all of these things. And this only applies to people that serve a lot of traffic. So Ruby on Rails has managed to make this not a problem for most people. Because we'll go into an architecture and there's like 40 boxes and they're having performance problems. Page loads take like 5 seconds. And they're like, we do 500 requests a second. I'm like, 500 requests a second per box? That's not bad. And that's all. No, they're like, no, 500 requests a second. It's across 40 boxes. And then the question is, at that point, you have to ask yourself, how much processing power is in this remote? Could I feasibly serve that much traffic off this remote? Because I know I could do the entire thing, 500 requests per second, designed correctly. Not a Ruby problem, but a data design, an application architecture design problem that Ruby propagates. It makes it easy to design things poorly from a data architecture and data flow level. Things are so easy, and Java does this too, so I can knock a little bit on Java. The language that has set a record at the number of function and method deprecations per release on Earth, and I don't think it'll ever be surpassed. Every 6 months, I run an app, and more things are deprecated. The problem is that so many container classes and collection classes and set classes are there that nobody ever thinks about which is the right one to use. They're like, I have 100,000 elements. I'm going to stick them in a hash. Like, really? Is a hash better than our red-black tree? Oh, premature optimization, dude. Really? What that answer tells me is that you have no idea what your problem is. You have no idea, because you should say, I understand my problem. I have 100,000 elements. This is the access pattern and the insertion pattern. So yeah, it seems like a hash table. That's fine. And then that's the premature optimization goes away, right? It's optimized in the documentation above it. The function uses a hash. Why? Because the documentation above it says, I have these assumptions of my problem, and that is why I selected a hash table. So then when someone comes back in and sees a hotspot in that code and says, hey, should we have a different algorithm? They have the assumptions right there in front of them and can match them with their current assumptions. There could be problems with the documentation, but they're pretty apparent at that point. So this is for people who don't run Ruby. So you guys are good on that. Understanding the bottleneck is pretty easy. A single machine can push a gigabit of traffic. Pushing more is not hard. But how to push 10, how to push 20, how to push 100 is an interesting question. Because there is an answer, and it's buying a really expensive load balancer. There are a lot of load balancers right now that can do 20 to 40 gigabits of wire speed load balancing. It's not a problem. It's a problem on the checkbook, though. It's extremely painful. There are other ways to do this because we can use routing. So routing supports extremely naive load balancing. And what we can do is actually treat our web servers as routers. We can actually use something like OSPF or RIP or something simple like that to announce the load balancers to the upstream router. You give them all the same IP address, and the router thinks they're all the same box. So a router is just going to balance the load across all of them. It'll distribute the load, which would explode because you'd have packets for some TCP sessions going different places. But routers also support things like source-based range routing and source-based hash routing. So what you can do is you say, I have all these links back here, and based on the hash of the source IP address, consistently choose one of those links. So then suddenly you have a router that can easily push 100 gigabits of traffic. It's an expensive router, but if you're pushing 100 gigabits of traffic, you actually have no choice but to have the router if you want them to go somewhere. So you already have the technology there, and now you have these Uber caches, which can actually be your load balancers. You can actually run routing protocols on your load balancers. So when you think, why would I build a new load balancing technology? It's actually they actually do a lot of this. So the sites that push a lot of traffic will actually run routing daemons on their Citrix appliances or on their F5s, so that they can push 20 gigabits of traffic across their 1 gigabit or 2 gigabit sustainable load balancers. Because there's always more demand than there is technology. The upstream uses hashed routes. User caches announce the same IP. This adds fault tolerance and distributes network load. It's not brilliant, but it works. And it's free. You have to have the router to serve the traffic. You have to have the machines to serve the content. You have to have the wires between them, I guess. I mean, it's all already there, so you can just run it. So your Uber caches could be load balancers. So if you're running multiple IP addresses and you're running different services on them, say you have a service on .67 and suddenly it gets really hot and it starts to saturate firewall states or it starts to saturate load balancers, something like that, you can actually isolate that service by having a surge network, which is a similar setup of load balancers and firewalls that basically inject the route for that /32 and pull just the traffic path for that /32 over onto a new network. So routing to the rescue. And you can set up a separate set of firewalls. It's interesting. You need to do some trickery in this that's complicated, but this is the same technique that they use for DDoS attacks. So if LinkedIn ever gets DDoS, your chances are your upstream provider. One common mistake of DDoS stuff, people are like, oh, I could do this and prevent denial of service attacks. You can never control traffic flow on the wrong side of a garden hose, right? If you hook up a pool filler to a garden hose and you try to rate limit it on the wrong end, you have to rate limit it on the big end. So if they're saturating your pipe, there's nothing you can really do to control that. You have to go upstream where you're not actually saturating the pipe to control the traffic. So this is the same technique that's used upstream to do that. Quickly on service decoupling, you guys already use this. I assume you use ActiveMQ to decouple services. Is that correct? Yes. What's that?
Not enough.
Not enough. So this is an interesting thing. Like most things on the internet, when it's shiny, everybody wants to do it, right? Like every other tool, it has its place. It's a very valuable tool, and do not use it when you don't have to, and always use it when you do, right? Simple tools. It's overlooked commonly. The philosophy is why do now what you can postpone until later. Everybody should understand that. Most programmers are procrastinators. The interesting part is that this mantra often doesn't break a user's experience, but it does require that you actually talk to user interface designers and user experience designers, right? To actually say, hey, you know, this little flow right here on the page, the way it's written, I can't decouple the service. And then, of course, they're going to be like, well, that's what the user wants. I'm like, okay, look, you don't actually know what the user wants. You never do. But you're really good at guessing. But work with me here and figure out, like, is there a way to decouple the service? So, like, one of the great examples of that is, like, I upload my 500 meg video, and it thumbnails it for me right there. Right? You know what? It's a 500 meg AVI file. I have to dissect the frames, find the first one that's probably not black or has some steady state. It's a lot of work, and I probably don't want to do it when the user clicks. And somehow, user interface designers and basically site flow, user experience specialists understand that, but they don't understand all the other stuff, like I'm going to send a message to my friend, and like before the button picks up and the page response, it's got to pop up on their side. It's like, really? Like, are you guys sitting side by side in a coffee shop and testing this? I mean, like, what's the point of that? There are ways to decouple this stuff. So the philosophy here is to break down the user transactions into the smallest possible parts, isolate what could occur asynchronously, queue the information that you need to complete the task, and then process the queues behind the scenes. This philosophy really matches well programming languages like Erlang, which is why a lot of the programming languages, why Erlang is used for telco stuff a lot. The only downside of Erlang is you have to program in Erlang. So, has anybody ever seen the distributed key value store comic? This is a great one. It's somewhat foul. You might have to edit it out. But there's a comic that says, oh, I heard we just installed a new distributed hash. How do I look up these key values? And the other guy's like, oh, you just write a distributed Erlang map and reduce process. It's like, Bob, did you just tell me to fuck myself? Like, yes, I did. You know, it's like, that's not the user experience you want even for a programmer. So it's a challenge. So this is called messaging. There are three genres of messaging that are popular. JMS, which is a really generalized one. It doesn't really describe the implementation. Spread, which uses an extended virtual synchrony model, which is really awesome for doing distributed systems like lock management protocols, election protocols, quorum protocols. This is what databases need to use to do distributed system, multi-master replication, and things like that. It has basically enough information about who's getting the messages and when they get them to establish views and groups so that you can do election protocols, which is not at all what you need to do when you say, can you do this later? AMQP, Advanced Message Queuing Protocol, is the common one. It was developed in the stock exchange vicinity to do all of the asynchronous processing that does trade transactions. There are a lot of implementations of AMQP. ActiveMQ is Java. OpenAMQ is C, and RabbitMQ. These are the three most popular that I'm aware of. We use ActiveMQ almost everywhere, except for when we want it to run really fast and really large, in which case we use RabbitMQ. ActiveMQ is much easier to use. I just spin up a Java process, jam it in a J2EE thing, and it just works. RabbitMQ is like black magic, but it scales extremely well. So how do you talk to them? The answer is over Stomp, and Stomp is the worst protocol ever written. When I gave this at ApacheCon, unfortunately, Brian McAllister was sitting in the front row. He wrote Stomp. That was bad. I didn't apologize, though. It's still bad. Stomp looked like HTTP a lot. HTTP is an awful protocol that they had excuse for making awful because they wrote it so long ago. Like the idea that I'm going to do really high volume network transactions and I'm going to tell the server, he's going to say, like, what do you want? I'm like, I'm not going to tell you. Not only am I not going to tell you what you want, I'm going to make you read every character until you find a /r/n to figure out what I want. Like, that doesn't make any sense at all. So if you look at really high velocity mail servers and things like that, they spend most of their CPU time in optimized assembly looking for /r/n's on the end of network traffic. And because SMTP was written in the same era. So I remember doing all of the assembly optimization for the Momentum product, which you guys just got. So you get to use that. That's cool. You use Stomp anyway, even though it's bad, unless you can use AMQP. If you're using all Java Stack, you can actually talk directly to that over AMQP, and life will be much better. The wire protocol for AMQP is designed specifically to be processor non-intensive. So how do you build a system like this? You use a message queue, and you have a job dispatcher. It's really simple. How many people here know what Gearman is or use Gearman? Anybody use Gearman here? One person knows what Gearman is. Gearman is a system that sort of does this. It's designed to be synchronous. You can obviously make it asynchronous by just lying and doing your job later. But it's designed to scale things out like that AVI, 500 meg AVI problem. When someone says, yes, it has to be this, and I have a big checkbook, you buy 100 machines, and you can distribute it out and get the answers back. So Gearman's a pretty nice product. Open source. Written by, I don't know if it's written by the same guy that wrote Memcache, but I think it might have been. And with message queuing, moderation, and all things, including moderation. When you decouple something, you have no idea what just went wrong. I spent the last 5 years of my graduate school looking at distributed system problems, learning one thing. I don't understand them very well, and I don't ever want to solve them. They're hard problems. I mean, even running a debugger is hard, right? I mean, multi-threaded, you run a debugger on a single-threaded process, and you hit step, you have an expectation, you sort of see what happens. In a multi-threaded process, you can sort of do it by instrumenting locks across things. But in a distributed system, there's no way to hit stop. Everything continues. And when you queue something and then go do something else, you suddenly have to do quality of service and monitoring on all of those queues to understand how deep they're getting, how quickly they're processing. Or otherwise, your user experience is going to go in the toilet, and you're not even going to know about it. So you have to can't deploy them blindly. You have to make sure you've thought about what can go wrong with message queuing technologies before you just jump in feet first. So the WTF section. These are actually fun. So acute scalability disasters are due to idiots. Don't be an idiot. Scaling is hard. Performance is easier. Performance is really not hard. How many people have done performance optimization here? Right, and it's it's fun. Basically, you wash, you rinse, and you repeat, right? And again and again and again. You get a profiler out and you figure out which thing is consuming the most amount of time. Not which is slowest, but which is the number of invocations times the time of invocation. Which one's the most painful? Can I optimize that if I can? That's where my largest fruits are. It's pretty easy. The cool thing is that high-performance systems are much easier to scale because you don't have to scale them as much. So one of the mentality problems with the Ruby on Rails community, which predates them, but it's the idea of that, like, you know what, I know I could do better than 40 requests a second per machine or 2 requests per second per machine, but I know I can do them, so I can just buy 10,000 machines. And it's like, do you know how hard it is to manage 10,000 machines? You know how often you have to renegotiate data center contracts at that point? Like actually provision equipment, figure that your machines are going to only last 36 months and cycle them in, then have heterogeneous hardware in there. Like you've just opened up an enormous can of worms because you're an idiot, right? So if you make a system that does 10,000 web requests a second and your capacity plan has you going up to 1 million, you're in a much better place than if you do one that has 100 requests per second, and that should be pretty obvious. So the faster you make things, the easier are the scale, and the cheaper they are to operate. So a simple example is you have a marketing campaign, and it's landing/page, right? Unfortunately, it's not actually landing/page. It's landing/page/, right? So you test it in your browser, and you don't even notice, most likely, right? This was amazingly embarrassing because we didn't notice this. So someone published this. I remember what it was. Either they gave them this and then marketing didn't like the slash. They tested it and it worked, so they published it without the slash. Something like that. Something bad that happened. This is a great example of idiocy. Another example of idiocy. Commit message, prevent caching here, right? You have a Swift gallery file, right? A flash file that what you're saying is not that it can't be cached. It's that if I have 2 users arriving within the same second, it's okay for it to cache, but outside 1 second, you can't cache it anymore. Like, what? This doesn't make any sense at all. One, are you going to deploy the Swift file every second? Is that the plan? Oh, no, I want to deploy it, but I don't want there to be any latency. Use an e-tag. You know, there are technologies for this. You should never prevent cache, you should control it. It's a way to blow your bandwidth bill out of the water. So a more detailed example is that we have 100,000 users, right? And we're going to have 10 million. This is the strategy, right? This is the plan. So what I'm going to do is I'm going to split it up into 100 different buckets. I'm going to shard it, deal with all that pain now, so I know how to use the system sharded. And I'll have 100 buckets, 1 million per bucket. Now I know how to scale to 100 million. It's awesome. It's great. So the problem is that I have no idea what my problem is. I know what my problem is with 100,000 users. I have no idea what it looks like. There is some margin for error, and there's an odd thing here. You would think, like, let's say I understand my problem for 100,000 users. I have a 5% margin of error. So as I go to 10 million users, that 5% margin of error obviously is more users. My theory is that 5% actually becomes 15%. As your problem grows, you actually understand how you know it less. So it's idiocy to do that. You have to have an absolutely profound understanding to design a system for 100-fold or 1,000-fold. So very few who have that. I would say that Google has that, and I've talked to a lot of Google engineers that go, oh no. You know how many this stuff has been redesigned 3, 4, 5 times as we understand how our theories collide with practice in beautiful flames. So you have to revisit this stuff. So we want to have a traffic spike on MSN, 3,000 visitors a second. We'll run through the math really quick. I'm going to do all the math and realize that I can serve all of the static assets off of 4 machines, including a failure, with a whole bunch of math to say if one fails, I still only want 70% utilization. It's great. The forgotten part, we'll do the math. It's 317 kilobytes per response, which is actually just under 8 gigabits of traffic. And this is 500 packets per second, which is 1.5 million packets per second. This is a lot of traffic for a data center that normally gets like 50 megabits or 100 megabits. The upside is that 20 of those assets per visit are static content. We talked about how to distribute that and serve it. We get it. We understand it. So the question is the remaining part, just the cool stuff page, the HTML of it, is 350 megabits alone, and it's 75,000 packets per second, which is perfectly manageable. Right? Our load balancers and firewalls, load balancers can do this all the way. Our stateful packet inspecting firewalls can do about 150,000 packets per second in this architecture, about a gigabit worth of traffic. So this is well within margin, which is perfectly manageable. But when marketing published the 302 page, it added 30,000 packets per second. We were by the skin of our teeth going through this, just because someone decided to remove a slash off of the end. And you have to go, you get the 302 response. People don't realize how many packets per second that can add to an architecture. It's pretty interesting. And I love Firebug because web designers, web developers, JavaScript coders actually care about this stuff now. Because they see the lines go backwards in the rendering time, and suddenly it's a little bit removed, but they get it, which is really good. So that's it. Any questions? Okay.